I'm Sam, and I'm an OpenSciEd teacher and facilitator. This lesson was a huge aha moment for me, and I'm going to tell you why. For a long time, I struggled with how to get students to see that breathing and burning are actually the same thing. In this video, I'm going to show you the key moves to help your students realize that every single cell in their body is essentially a tiny engine. So, how did we get here? During the last lesson, we figured out that burning food is a chemical reaction with oxygen that releases energy and produces carbon dioxide and water. In this lesson, we're wondering, does this same reaction actually happen inside of us? And to figure this out, we're going to do two things. One, we'll follow the path of air in our lungs and analyze oxygen and carbon dioxide levels in the blood. Let's take a look at a lesson at a glance. This lesson is a 3-day lesson that takes about 25 minutes of prep time, which includes setting up for a hands-on lab with BTB. If you don't have BTB on hand, that's okay, because there's a great video on the OpenSciEd website that you can use to show your students instead. Because of the depth of data in the Teacher's Edition, I want to help you to see the 4 loops that drive the sense making in this lesson. Let's take a look at those loops together. The first loop. In this first loop, which are parts 1 through 3, we're going to look for the evidence of breath. Students will use BTB to test their breath. We're going to figure out that we are exhaling CO2, a known product of the burning reaction. Well, if we know that carbon dioxide is coming out of us, we need to figure out how oxygen and carbon dioxide actually get in and out of the body, which brings up loop 2. Loop 2 is part 4, where we're going to map the path. We will analyze the alveoli and molecule sizes. We will figure out that oxygen and carbon dioxide are small enough to pass through the lung membranes and into the blood. And if these gases are entering the blood, then where is the blood taking them? That brings in loop 3. Loop 3 are parts 5 through 7, which is finding locations. Students will analyze blood data showing oxygen and carbon dioxide levels in different body locations. What we're going to figure out is the reaction isn't just in the lungs. It's happening in cells throughout the entire body. But if this reaction is happening in our cells, we need to know if the rate of that reaction changes when our body's energy needs changes, which motivates loop 4. Loop 4 is all about energy demand, which is parts 8 through 11. In parts 8 through 11, we'll analyze data on oxygen and glucose use during rest versus exercise. We'll figure out that this reaction, which we name cellular respiration, happens all the time, but speeds up when we are active. And that will bring us into the next lesson, where we've now figured out how cells get energy, and we'll finally be able to explain why McKenna is feeling so fatigued. So let me summarize what we figured out by day. On day 1, we figured out that molecules of oxygen and carbon dioxide pass through our lungs and into our blood. On day 2, we realized that the chemical reaction is happening in cells all over our bodies. And on day 3, we conclude that the reaction happens all the time, but speeds up significantly when we're active. Let's dig into some key moments. The first key moment happens in part 2, which is the BTB investigation. Students see that the blue liquid turned yellow. This is visual proof that carbon dioxide is actually leaving our body. During this part, I find that connecting to lesson 11 can be very helpful, because if carbon dioxide is coming out of us, The reaction must be happening inside of us. A second key part is in part 6, where students analyze oxygen and carbon dioxide levels in the blood. See, my students often think that the reaction is happening in the lungs because this is where we breathe. To address this, have students compare location 3, which is blood going to the body, to location 4, blood returning. And try asking the question, if the blood was doing the burning, why is the oxygen still high at 95 at location 3? This proves that the blood is just the delivery system, and the burning happens once the fuel reaches the cells. Another key point is in part 10, which is interpreting activity data. The key takeaway is that increased activity causes or increases the need for energy, which speeds up the rate of the chemical reaction. That's the effect, right? So we're really looking at cause and effect. During the sense making, have the students use the I2 strategy, which we've already practiced several times throughout this unit, for the glucose graph. If students struggle to connect to their own bodies, ask, well, why do we breathe fast in PE? It's really to get more oxygen to the reaction. And why might you feel hungry after playing? Remember, it's because your glucose levels dropped after you burned it for the energy. We also might want to make a math connection. The steeper the drop, the faster reaction is happening. So where do we go from here? We really want to celebrate. We figured out so much that we can probably use what we've learned to explain some of McKenna's other symptoms. Let's take a look at some material management tips and tricks that I used during this lesson to help it go more smoothly. In part 2, when you do the BTB test, test your tap water. If it's not blue, let it sit out or add a tiny drop of base to reset it. And I've had a lot of questions about what kinds of soda water works for testing. Any kinds of soda water will work. And remember that the BTB solution can always be reused. Just let it sit out for a little while and it will eventually turn back to blue. In part 8, when we do the initial ideas discussion to make predictions, teachers often ask where the guide switches fuels, right? Because in the previous lessons, we've been talking about fat, and now all of a sudden we're talking about glucose. So where does this happen? This really happens in part 8. Don't feel like you missed a page. The guide intentionally uses that fat burning lab as macroscopic proof that food plus oxygen equals energy. Then, in lesson 12, it asks students to apply the same logic to the molecules that they actually saw moving through McKenna's blood earlier in the unit. That was glucose. Remember, in lesson 4, we see that it's glucose that's moving through the body, not fat. So, I also like to tell the teachers to show a side-by-side of glucose molecules and a fat molecule. They're both made of the same C, carbon, H, hydrogen, and O, oxygen atoms. If fat can burn, so can glucose. Lesson 12 isn't replacing the fat story. It's just showing us that the specific fuel that is currently on the delivery truck, the blood, right now is glucose. Word wall management. In this lesson, students will earn the word cellular respiration, but really wait until part 11 to co-create that definition together. Poster management. Keep your system mapping chart from lesson 8 handy so that we can add the respiratory connections in this lesson. So, to summarize, we're moving from systems to cells. Every single cell in McKenna's body is a tiny engine performing a chemical reaction to help keep her alive. We have figured out so much that we can now use this to explain her other symptoms. I hope to see you in the next lesson. Happy teaching!